Okay. And at least I remember to start recording. But yeah, let's try to not have this be the norm. That when the clock strikes 1, then we're all here and can get going, so we don't have that lateness creep that I was talking about earlier. Okay, now we have everybody but 1. And then that one told me they were running late anyway. Okay, now, so I'm going to continue into the next section. We'll see how it goes, and maybe there'll be some time at the end for homework questions. Although, actually, if not, I don't really have a whole lot to cover on Monday. Now, Monday is when the first assignment is due. As far as when it's due, well, some of you know that I'm not really rigid about dates anyway, and if it's due February 1st, it can be turned in any time on February 1st. So I would strongly encourage you to, if you don't have questions on homework ready today, certainly have them ready for Monday, because we will definitely have time to go over them then. Okay, so let's do the old screen share. Okay, and when I opened these notes right before class, I realized that I had not even updated the title, 3.3 Special Matrices. Like, okay, that bodes well. Okay, but hopefully the content of the notes themselves is okay. All right, so what we've seen so far is we're solving AX equals B, and we're performing, or we're accomplishing that by performing Gaussian elimination on A, and then using forward and back substitution with the LU factors after that. So we have this process, and that will work for any non-singular n by n matrix. So you might think, oh, okay, well, we could just stop here. Well, no, because we do want to try to do things better if we can, at least in certain circumstances. So for general purpose, yes, this is usually the method of choice, Gaussian elimination, with partial pivoting in particular, because that strikes a good balance between ensuring more robustness with respect to round-off error and so forth, but also not adding too much overhead in terms of computational effort. So what about certain classes of matrices for which faster solution is possible? So I'm going to focus on some of those. And these classes of matrices do come up in very important applications. So these things are definitely good to know. So there's really two classes of matrices I'll focus on. One is banded matrices, and then the other is symmetric matrices, and most important, symmetric positive definite matrices. So for these cases, we have specialized methods. Okay, so what I have here, this matrix B, is an example of what is called a banded matrix. So here we have a main diagonal, so -2, 1, 3, 1, -2, and then I have a subdiagonal, so the entries that are right below the main diagonal, so 1, 4, 11, 3. And then notice that everything below that one subdiagonal is 0. And then if I go to the right of the main diagonal, I have this first super diagonal, 1, 8, -2, 1. And then I have another super diagonal, 5, 4, 7. Everything above that is 0. So what we can say is that this is a matrix that has a lower bandwidth of 1. So here's the formal definition of lower bandwidth. Really what that means is lower bandwidth is equal to the number of subdiagonals that have non-zero entries. So in this case, just 1. This matrix also has an upper bandwidth of 2. So here's the formal definition for upper bandwidth, that whenever, if matrix is 0, whenever a column index minus a row index is greater than that bandwidth, that if the entry is 0, then that's the upper bandwidth. So here we have two non-zero superdiagonals, so the upper bandwidth is 2. Okay. All right. All told, we have, in this example, 4 diagonals that have non-zero entries. So we have so the total bandwidth is 4. 1 for the subdiagonal, we have 2 superdiagonals, and then you include the main diagonal in that, so we have a total bandwidth of 4. So if P is the upper bandwidth, Q is the lower bandwidth, then P plus Q plus 1 for a main diagonal is the bandwidth. So now for n by n matrix, there's as many as n minus 1 superdiagonals. There's as many as n minus 1 subdiagonals. So the bandwidth is always at less than or equal to 2n minus 1. But if it is less than 2n minus 1, then we say it's banded. What we care about most is a case where you have a matrix, n by n matrix, where n is large, but the bandwidth is particularly small. Because that's when solving Ax equals b by Gaussian elimination gets a whole lot cheaper than the general case. So one example of this is if the upper and lower bandwidth are both equal to 1, then we have a tridiagonal matrix. You have 3 non-zero diagonals: main diagonal, 1 superdiagonal, 1 subdiagonal. So if you have an n by n matrix, but the bandwidth is order 1, so it's some small constant independent of n, that's when we can really have substantial gains in efficiency when solving Ax equals b. And here's one of the best known tridiagonal matrices. So you may have seen this matrix in other classes with me, or you most likely will later, coming from numerical methods for differential equations. So this matrix, it has -2s on the main diagonal and then 1s above and below. So this is a matrix that comes from the center difference approximation of the second derivative, because second derivative at a point x is approximately equal to -2 times the function at x plus 1 times the function at x plus delta x plus 1 times the function value at x minus delta x. So there are a lot of matrices like these that come about from finite difference formulas for derivatives, and this is very important for numerical solution of differential equations. So this matrix is banded and tridiagonal. We have an upper and lower bandwidth of 1. And here I'll show you, if we compute the LU factorization without pivoting, and it turns out that it is possible in this case, that no pivoting is needed. But this is what we get. So this matrix on the left is L, unit lower triangular, so 1's down a diagonal, and we only have 1 non-zero subdiagonal. And then we have, in the matrix U, it's upper triangular, here's the main diagonal, and then we have 1 non-zero superdiagonal. So what we see in this example is that the lower bandwidth of L happens to match the lower bandwidth of A, and the upper bandwidth of U happens to match the upper bandwidth of A. So one of the homework problems gets into the more general case of what happens with the matrix of general upper bandwidth P, lower bandwidth Q, in terms of what happens with the LU factors. And that's where you think about how many row operations are you having to perform when the matrix is banded, and how many entries will those row operations affect when the matrix is banded. Now, when you have a matrix like this, that especially one that's tridiagonal, notice if I store this matrix in the usual way in memory, a two-dimensional array, I'm storing a bunch of zeros. Now here, in this case, it's just 5 by 5. Now imagine if a matrix is, say, not even all that big, 100 by 100. So that's 10,000 entries, but all of those entries are 0 except for roughly 300 of them, actually 298. So that's really wasteful to store all those zeros. So a better choice is to have vectors that represent each of the diagonals. So I could have one vector for a main diagonal that has these -2s. I've had a vector one with one element less for the super diagonal, another one for the subdiagonal. Now in MATLAB, there's two data structures for matrices. There are full matrices, which is a conventional two-dimensional array, and there are also sparse matrices, where all that's done is it stores a list of the non-zero entries. And there are specialized functions for working with full versus sparse. Like the command in MATLAB EYE generates a n by n identity matrix. That's a full matrix. But there's also SPEYE that generates a sparse identity matrix. That's just a list of the ones on the diagonal. So it's important to be aware about commands for sparse versus full matrices, because there are a lot of applications where you might be working with an extremely large matrix, thousands of rows and columns, but then if it's sparse, you save a whole lot of storage and your code will run a whole lot faster. Okay. So for a tridiagonal matrix, so here's an example of how Gaussian elimination can proceed. If I have a main diagonal in the vector A, subdiagonal in the vector L, and then a super diagonal in the vector U, then this is Gaussian elimination for a tridiagonal matrix. Now, if you remember the algorithm for Gaussian elimination that I would have shown you a week ago for a general case, that algorithm involved a whole lot more. There are 3 levels of loops for our order n-cubed operation algorithm. But here we just have one loop that runs n-1 times and only performs 1, 2, 3 floating point operations. So whereas Gaussian elimination in a general case takes about 2/3 n-cubed arithmetic operations, for a tridiagonal matrix, it's roughly it's actually a 3n-3. So 2 orders of magnitude less work in the tridiagonal case. Now, how this algorithm was obtained is, let's see. I wonder if I have time to do that. I think I can. All right. And I probably shouldn't do this when I'm not feeling the best, but it's fun, so I want to give it a shot. Okay, I'm going. You can't see this, but I'm going to the notes from a week ago where I had the algorithm for Gaussian elimination, and I'm going to copy that in here. Okay. Okay, so here we have, I have some notes in here that were from that class. Let me reduce that clutter. Okay, well, for one thing, this is Gaussian elimination that works in the augmented matrix. We don't really care about working with B at all, so I'm just going to get rid of this line right here. Bye. Okay. So now I want to adapt this to the tridiagonal case. Now, the outer loop is exactly the same because The outer loop loops over columns, and you need to do something in this loop for every column in which you have a non-zero entry to eliminate. And that's still the case with the with a tridiagonal matrix. But now, this next loop, we're in column J. We start below the diagonal and go all the way to the bottom. And we need to eliminate all those entries. But if we look at a tridiagonal matrix, let's say, for example, I'm in like this column. Here's my diagonal entry. I only have to eliminate one entry below it, and that's true for each of these columns. So that's what it means to have lower bandwidth P, or sorry, lower bandwidth Q. I only have to look at Q entries per column at the most, and then like ending columns even fewer than that. So what I can do is I would have I equal to only j plus 1. It doesn't have to iterate all the way to n. So I'm going to get rid of that loop. Okay. Whoops, did I delete the wrong one? Yeah. All right, and then I'll unindent. Okay, so throughout this, I is just going to be equal to j plus 1. So I can fill that in wherever I have it. Okay, and then the same thing is true wherever I have I down here. Okay. All right, so now we're down to order n squared algorithm. But now, what about when I perform the row operation? So if I go back to this example right here, like say I'm eliminating this entry. So I'm going to take a multiple of this row and subtract it from this row. But notice, when I subtract this row from the next one, I have all these zero entries here that will not affect the row below it at all. How many entries will be affected? Like this entry is right above the one I'm eliminating. I'm not even performing that computation. This entry, I multiply it by, in this case, minus 1/2, and I subtract from this entry right here. So here is where I'm actually doing something. But this is only happening in column j plus 1. So that column is the only one I need to act on. So that means throughout here, I can get rid of this loop. And then wherever I see k, k will only be equal to j plus 1. Okay, so from taking into account that because of the lower bandwidth of 1, I only needed to eliminate one entry per column. And then due to the upper bandwidth of 1, I only needed to update one entry per column. When I get down to here, now we see how the algorithm does so much less work. That here we have those 1, 2, 3 floating point operations for each of n minus 1 iterations. Now, I'm going to leave that there. So now this algorithm, as shown here, still works as a conventional two-dimensional array. And I don't want to do that. I want to use the vector storage. So wherever you see a diagonal entry, so row and column indices the same, that's referring to the vector A that stores the main diagonal. So that would just be A, like AJ plus 1. And here we'd have A, J. Now, any place where we have a row index greater than the column index, that is a subdiagonal entry. So remember, row index greater than column index is always in the lower triangle. So this would be entry J of L. Okay, and sure enough, we have LJ over AJ in both places. If we have a row index less than the column index, that would be above a diagonal. This is super diagonal. So that's an element of a vector U. So this would be UJ. And the only thing left is like whatever you name the multiplier. But remember, multipliers are supposed to be stored in the lower triangle. Notice here, row index greater than column index. So really what we'll do is we'll just overwrite LJ with the multiplier, because that's what is stored in the matrix L anyway in the LU decomposition. And sure enough, I have recovered the algorithm. So now these two algorithms match exactly. All right, so I just wanted to show you where that comes from. Oh, I have a LaTeX error here somewhere. Oh, okay. Are any questions about what happened there?
Yeah, sorry, I just jumped in. So the point of the vector storage is it's only storing non-zero values, or like non-zero values that aren't important. You know, like there could be a zero maybe within the.
Yes.
Yeah, okay.
So it stores every entry in those diagonals where you might possibly have non-zero entries.
Right, okay.
Yeah, okay. All right, other questions? Alrighty. Yeah, so after this is done, the vector L holds the multipliers, like in the regular storage of L from LU decomposition, and then U has the updated superdiagonal entries. Although actually, I don't even need to see updated. Notice this algorithm never changed U at all. So the only part of U that got changed was the diagonal. And that's also an artifact of the upper bandwidth. Now, the same thing goes for this is a forward substitution, and this is back substitution. So if you took the algorithms, the original algorithms for general case of forward and back substitution, and stripped them down to account for bandwidth in the same way that I just did for Gaussian elimination, these are the algorithms you come up with. So these algorithms in general case are on the order of n squared floating point operations, but here they're on the order of n. So you can solve a tridiagonal system in order n operations, which makes a huge difference when n is large. Now, there's one problem, though, with banded matrices, and that is pivoting. And pivoting is something generally you want to do. But if you perform pivoting with a banded matrix, it destroys that banded structure. So you could introduce new non-zero entries into the matrix. You're getting non-zero entries outside of the original band. And this phenomenon is called fill-in. So we have a nice sparse matrix with a very helpful structure, and we don't want to lose that. So what do people do in this case? One option is changing a pivoting method. Like, for example, with partial pivoting, you look in your column and you find the largest entry and you swap that into the diagonal position. Maybe you don't insist on the largest. Like you're not going to require that the multipliers are less than or equal to 1. Maybe you require that they're less than or equal to some other factor. So then you're more flexible in terms of what swaps you make. So you're still trying to contain the size of the multipliers, but not as stringently as in the general case. So maybe you get larger multipliers, but then if your matrix remains sparse, then you still get the benefit of that sparsity. So this is significant area of research in numerical linear algebra, pivoting schemes for sparse matrices. I want to mention a faculty member from another institution, Tim Davis, who he was at University of Florida, but I think now he's at somewhere. I think it's like Texas A&M or something like that. But I actually think he implemented a lot of the sparse matrix routines in MATLAB. So his whole research is all about algorithms for solving AX equals B for sparse matrices and having good pivoting schemes and things like that. So things we all choose to build our career on. Okay, so it's kind of funny how for general matrix pivoting good, banded matrix pivoting bad. It's kind of so these sort of things that happen when you have when you change a problem by adding these kind of assumptions. Okay. That's why it's nice to have a matrix such as this one. It can be proven that pivoting is not necessary for this matrix. And look at the multipliers that we got. These multipliers are less than or equal to 1 in absolute value anyway. So that worked out nicely. Okay, so that's the story with banded matrices, that you can save a lot of expense in Gaussian elimination, but be careful about pivoting. You might not want to do it or change how it's done. All right, so now for the remainder of the time, I will talk about symmetric matrices, and more specifically, symmetric positive definite matrices. So when you have a symmetric matrix, that means that it's equal to its own transpose. So in other words, if you reverse the sense of rows and columns, the matrix does not change. And it's symmetric. So basically, the entries above a diagonal are mirror images of the entries below a diagonal. And it turns out that when a matrix is symmetric, it's possible to, again, solve AX equals B more efficiently than in a general case. So there's a couple of factorizations that I want to tell you about for a symmetric case. So the first one is called the LDLT. Well, technically LDL transpose, but people often just say LDLT. Now, so suppose we have this LU decomposition. Now remember, L is unit lower triangular, and U is unit lower triangular, and U is upper triangular. So what I could do is if I basically factor out the diagonal from U. Now, because it has an LU decomposition and A is invertible, U has to be invertible also. So all of these entries must be non-zero. So what I can do is I can factor U into the product of this diagonal matrix D, and then whatever's left over, which is this D inverse U. So that matrix is going to be unit upper triangular, because if you look at the entries of this matrix here, D inverse U, if I set I equal to J, then I have UJJ over UJJ, which is 1. So the diagonal entries of this matrix are 1. So then I'm going to call that matrix M transpose. So D inverse U is unit upper triangular. I'm going to label it M transpose. Therefore, M is unit lower triangular. So now I have this modified factorization of A. So instead of LU, I have LD M transpose, and L and M are both unit lower triangular, and then D is diagonal. So this is the LDMT factorization. So it's really just a modification of LU, because the L in both cases is the same. Now, for a general matrix, LDMT is actually not interesting, just because it's just a slight modification of LU. But where things become interesting is the case where A is symmetric. Because let's suppose that A is symmetric, then LDM transpose is symmetric. Now here I'm using a property that the transpose of a product is a product of a transposes in reverse order. So LDM transpose is the same as MDL transpose. So now I'm going to perform similar manipulations as to what I did last class, where I showed that the LED composition is unique. So I can take, if I've set these two equal to each other, and I multiply on the left by M inverse, and I multiply on the right by M inverse transpose, which is what the minus T means, then I have this situation, that I have M inverse L times D is equal to D times M inverse L transpose. Now, L and M are unit lower triangular. Therefore, M inverse is unit lower triangular. Therefore, M inverse L is unit lower triangular, because inverting and multiplying does not change triangularity. Therefore, M inverse L transpose is unit upper triangular. So just like what happened last class, we have a lower triangular matrix here equals an upper triangular matrix here. Therefore, they must both be diagonal. D is already known to be diagonal. Therefore, M inverse L is diagonal. But we already know that this matrix is unit. So it's identity. Therefore, L is equal to M in the case where A is symmetric. So now this is a factorization we have. A is equal to LDL transpose, where D is diagonal, L is unit lower triangular. Now, why is this helpful? Well, for one thing, storage, because now I can represent A using about half as many entries, because since L is unit lower triangular, I only have the strictly lower triangular part that I need to store, and then I have the n diagonal entries of D. So the interesting entries of L and D turns out to be about, it's like n times n plus 1 over 2. So instead of representing all n squared matrix entries of A, I can represent A using about half that many. And that's going to be helpful for when I want to solve AX equals B in the case where A is symmetric, and using this factorization. Questions up to this point? Now here I have a symmetric matrix. So if I perform Gaussian elimination, I only have to eliminate this 2 down here. So I compute the LED composition. I subtract 1/2 times this row from this row, and this is what I get. So here's my L and here's my U. So now what I do is, if I factor out the diagonal entries from this matrix, I have a diagonal matrix with 4 and 2 on it, and then what's left over is this this unit upper triangular matrix, which is just the transpose of this. So this is L, and this is D. So you can think of it this way: I'm applying a row operation to eliminate this entry, and that gives me L. And then I could, if I want to make this matrix diagonal, I perform a column operation on this matrix. It's basically the transpose of a row operation that I did here. And that gives me this factor and then this diagonal matrix here. So sure enough, notice that these are the same matrix, except for just transposes of each other. So you could think of it as one way to compute the LDLT factorization. You go ahead and perform Gaussian elimination like normal, but as you perform these row operations, you also perform a corresponding those same operations as column operations on the matrix U that you're getting, and then you get the L transpose on the other side, and then you have a D in the middle. So that is one way to get the LDLT factorization, but it's not really the most efficient. But there is another way that I can discuss in a little bit. Now, once you have the LDLT factorization, how do you solve AX equals B? It's kind of like with Gaussian elimination and the LU decomposition. You solve, in Gaussian elimination, you solve Ly equals B, and I should say after Gaussian elimination, and then you solve UX equals Y. So here you start the same way, Ly equals B, and then instead of UX equals Y, you solve a diagonal system, which is very quick, and then you also solve an upper triangular system using back substitution. So really, these two steps put together are essentially equivalent to back substitution that we saw before. Okay. Now we do have an algorithm here for efficiently computing the LDLT factorization. I'm not going to go through the details of this just because I really want to focus more on the material to come, which is on the symmetric positive definite case. I will tell you I did not assign any homework problems from LDLT. This is the overall algorithm right here that, okay. And the interesting thing about this algorithm is it only deals with the lower triangular portion of A. So notice the only time entries of A are mentioned is right here in this line, where now here I'm using MATLAB syntax to describe taking a portion of a column. So I'm taking A, column J, rows J through N. So from a diagonal all the way to the bottom. So then I set that equal to UJ, and then I work with UJ after that. So this algorithm successfully exploits the symmetry of A, so accessing only the entries that it absolutely needs to compute the LDLT factorization. So what's interesting is it takes, because it only accesses half a matrix A, it only takes half the operations. So Gaussian elimination takes roughly 2/3 n cubed operations. LDLT requires about half that, so roughly 1/3 n cubed. So having half the distinct entries in the symmetric case leads to half the operations for anything you do in solving AX equals B. So this is why it's important to take into account whatever properties you know your matrix has. That, yeah, if you have a symmetric matrix, yes, you can solve AX equals B using ordinary Gaussian elimination of partial pivoting. But now you see that you are wasting operations, so you should choose a method that actually works with that symmetry. Okay. Now, this algorithm does not include pivoting. One thing to be careful about is if you are going to do pivoting, if there's a need to swap rows, you should also swap the corresponding columns. That way, symmetry is preserved. Because if you lose the symmetry, then you lose the gain in efficiency that symmetry is supposed to give you. So never do anything to lose that. Okay. Now, during the rest of the time, I'll talk about a very important subcategory of symmetric matrices. So symmetric matrices that are also called positive definite. So when a matrix has an LDLT factorization, the entries of D should be need to be non-zero. But now I'm going to focus on the case where those entries are actually strictly positive. So here's a definition of a symmetric positive definite matrix. So a symmetric positive definite, if A, first of all, it's symmetric, and second, this inequality holds. So X transpose AX must be strictly positive for any X that is non-zero. And you can think of a symmetric positive definite matrix as a generalization to n by n matrices of a notion of a positive number. So as opposed to other possibilities like a matrix A having all entries that are positive or something like that. So when a matrix is symmetric positive definite, it is still allowed to have some negative entries. They can't be on the diagonal. But as long as this property holds. Now I want to point out the definition requires this and symmetry. So there are matrices that are not symmetric for which you can show that this property holds, but you don't get to label those as positive definite. So we're assuming symmetry all along. Now, there's some interesting properties that a symmetric positive definite matrix has. So its determinant is positive. Diagonal entries are all positive. And you can see that from this definition here. If I set X equal to column of identity, then X transpose AX is just a diagonal entry of A, and that's required to be positive. Okay, so actually I'm going to make a note of that here. EI is the ith column of identity. We're going to see that from time to time throughout the semester. So I'll be harping on that again later. But so like E1 is vector 1 followed by zeros. E2 is 0, 1, and then all zeros, etc. Also, the largest entry of a matrix has to be on a diagonal to ensure that this happens. This could be taken as a equivalent definition that all of the eigenvalues of A are positive. We'll deal more with eigenvalues later, but that's one property of symmetric positive definite that comes in handy, that positive eigenvalues. Okay. Now, it's actually not easy to check if a matrix is positive definite. In some cases, you can rule it out. Like if you see a entry in a diagonal that's non-positive, and you can tell right away it's not positive definite. But what you can do is you can check something I brought up last time, the leading principal submatrices of A, like A11 or this upper left 2 by 2 block. Like this is the upper left K by K block. If they all have positive determinants, like so every single one of them, then so if and only if that is true, then A is symmetric positive definite. Now that's costly to check because computing all these determinants is computationally expensive. So there is no super efficient way to check, unfortunately. Now, this kind of condition came up on Monday because when I was explaining when does the LU decomposition exist, well, that means these same determinants must be non-zero. So because in the symmetric positive definite case, these determinants are non-zero, in fact, are strictly positive, that proves that the LU decomposition of a symmetric positive definite matrix always exists. So it is never necessary to pivot to avoid dividing by zero. So you can go ahead and use Gaussian elimination to solve Ax equals B in a symmetric positive definite case, and know if you don't have to perform row interchanges. Now, it might still be beneficial to reduce round-off error, but you can trust that Gaussian elimination will never break down in that case. And it's also been shown that the accumulation of round-off error is not as severe with symmetric positive definite case as in the general case. But Gaussian elimination is wasteful on a symmetric positive definite matrix because Gaussian elimination does nothing to take into account the symmetry of a matrix. So we want to find an approach to solving Ax equals B that does that. Now, we can do LDLT, but I want to show you another approach that's just for symmetric positive definite, and it's called the Cholesky Factorization. So Cholesky is kind of similar to LU. That A is factored into a product of G that's lower triangular, and therefore G transpose is upper triangular. So we still have lower triangular times upper triangular. It's just that now we know that the factors are transposes of each other, which takes into account the symmetry. And we also require that the diagonal entries of G must be positive. Okay. So computing Cholesky factorization, like LDLT, requires only about half as many operations as LU, because we're taking advantage of a symmetry. So how do we figure out for Cholesky factorization? So what I'm going to do is show you an example in which I take a symmetric positive definite matrix. And notice there are negative entries, they're just not on the diagonal. And we'll actually go ahead and compute this Cholesky factorization by hand. So what I do is I have A equal to GG transpose, where currently G is unknown. So if I write out A equals GG transpose, and I require that G is lower triangular, this is what that factorization looks like on an entry by entry level. So now what I can do is I can carry out the matrix product of these two, and I equate that to A. So for example, if I compute the 1-1 entry of this product, I go across the first row, down the first column. So I have G11 squared, and then everything else is 0. And I match that to A11. So A11 is G11 squared. And I go ahead and do this for all the entries of this matrix. And now I have this series of equations satisfied by all the entries in the lower triangle of A. I'm not bothering with the upper triangle because of symmetry. So this is how the entries of A relate to the entries of G. So I can use these equations to solve for all the entries of G. I just have to go in the right order. So a natural starting point, of course, is this. It gives me G11. Once I have G11, I can fill that in here. And then I can solve for G21, G31, G41. I can also use G21, put it in here, and then I can solve for G22. So all the entries that I compute as I go through these steps, I can then fill those values in down here. So each one of these equations only introduces one new entry of G. So what I do here is I just go ahead and step through the process of solving for all these entries. Notice I figure out the first column of G right off the bat after computing the square root. Then I go to the second column. And oops, something is. Okay, hold on. Okay. So now what I'm doing, like when I go to A22, I update it. I have G21 already. So now I go ahead and subtract G21 squared off. Here of A32, I know this term because I have G31 and G21 from before. I subtract it off. Same thing with A42. I know these already. Subtract them off. So these three lines deal with the second column of A. So now, whatever came from a first column of G, subtract off those contributions. So that's what I do in these three lines right here. Then I update column 3 and column 4, again by subtracting off any contributions that came from the first column of G. Now, I can finish the second column of G. I take a square root to get G22, divide by G22. So I want to point out the similarity between these steps right here that gave me the first column of G, and then these steps that give me the second column of G. So I square root, divide, subtract off contributions from A in the later columns, the columns I've not gotten to yet. Then I do the same thing, square root, divide. Then whatever contributions from a second column of G, I subtract off from the later columns. So here I'm updating column 3 of A in the first two lines. And then the last line, I update the fourth column. I only care about the diagonal entry in the fourth column because all the other entries in the fourth column are from the upper triangle, which I'm not dealing with. And then I have square root divide, subtract off a contribution of a third column of G from a fourth column, and then I just have a square root. So now I'm done, and I have the lower triangle of G completely filled in. And this is what the Cholesky factorization looks like. Yes, I made the numbers work out nicely. So A is equal to G times G transpose. Any questions about how that algorithm unfolded? And I'll come to this part in a bit, but I want to show you, this is the general algorithm that mimics what I did in the example. So you're iterating over all the columns. So you compute first column of G, then second column of G, etc. You always start with a square root of a diagonal entry that you have in that column. Then when you go through the rest of a column, you're always dividing to get Gij. You take Aij divided by the diagonal entry that you just got. Then here's where you update A by subtracting off contributions from column J of G. Because notice you have Gij and Gkj. These are entries of the jth column that we've just computed doing this. That's what we subtract off. So then the modified A is what's used in the next iteration, where we can do the same thing, square root and then divide. Now, I want to show you what this means in terms of what are called outer products, which is likely something that you haven't seen before. And okay, so I'm going to fill in some extra material here. Whoops. I hate when it does this. Okay. So just in general, if you have two vectors u and v, if I have u transpose v, so a transpose is on, I should say these are, I have to require that these are column vectors, which is the default. If you see a vector in the numerical linear algebra setting, it's assumed to be a column vector. So the inner product is u transpose v, and you can remember that because the transpose is on the inside. There's a dot product. In this case, u and v have to have the same length. And the dot product, inner product, is just a number. On the other hand, if I compute, whoops, that's weird. I don't know why it's insisting on behaving like this. It's kind of ticking me off. Okay, that's better. If I do u v transpose, is their outer product. And that is a matrix. And I'll write out what that matrix is. I just realized I don't have much time left. Okay. So, all right. Okay. So, unlike a conventional or general matrix-matrix product, an outer product, each entry is just a product of two numbers instead of a sum of products. Okay, something is wrong here. Okay, u to the n. Okay, and finally u m v1, u m v2, u m v n. Okay, so that's what an outer product looks like. Notice that the first row is a multiple of u1, second row is a multiple of v2, and so on. First column, multiple of v1, second column, multiple of v2, and so on. So all the rows are multiples of each other, all of the columns are multiples of each other. Okay. Now, if and how we can use outer products to describe matrix multiplication, if A has a column partition, A1 up to AN, So if there's a column partition of A and B is also partitioned by its rows, we have like B1 transpose up to Bn transpose, or B, not V. Then I can write the matrix product AB is equal to a sum of outer products A1, AJ, BJ, transpose. So this is the outer product description of matrix multiplication, that AB is a sum of outer products of each column of A with a corresponding row of B. So now A is equal to GG transpose. So I can write A as a sum of these same kind of outer products. It's just that the vectors are the same in this case. Based on the columns of G, which are also the rows of G transpose. So this perspective is used to describe the algorithm, or to derive the algorithm for Cholesky decomposition. Because what I do is I compute the first column of G right off the bat, and then I'm subtracting G1 transpose from A. So what I'm doing is, in the algorithm, I'll show you from the example, when I'm doing all of this, this is subtracting off G1 transpose from A. So in other words, all the contributions of a first column of G to A come out here. Here I'm subtracting G2 transpose from A. Now, why is that helpful? Because the fact that G is lower triangular, that G1, the whole column can be non-zero. G2, the first entry must be 0. G3, the first two entries must be 0, and so forth. So what that means is, okay. The outer product, GJ transpose, can only contribute to the n minus j plus 1 times j plus 1 lower right block of A. So G1 can affect the whole matrix. G2 can only contribute to the n minus 1 by n minus 1 lower right block of A. So the idea is we compute G1, subtract off G1 transpose, then the first row and column of A, I'm done with. I can discard them. So I can focus only on that lower right part, as has one row and column less. And then I can work on that in the same way to get G2 as I did in the whole matrix to get G1. So there's like a recursiveness to it in a way. And that's actually what I described here. So I use its first column to get G2, subtract off G2 transpose. Then I'm working on the lower right n minus 2 by n minus 2 block. Use its first column to get G3, and I keep going. And that's what leads to the whole algorithm that we see here. Now, suppose A is not symmetric positive definite. What will definitely happen, one of two possibilities. Either you get a negative entry here, you're taking the square root of a negative number, or maybe AJJ is 0. So you get 0 here, and then probably divide by 0 here. Either way, the algorithm breaks down. So using a Cholesky algorithm is actually a good way to check if A is symmetric, positive, definite. Just go ahead and have MATLAB try computing a Cholesky factorization. If A is not symmetric, positive, definite, then it fails. So that's really just as efficient as any other approach you could come up with, like checking the leading principal submatrices. All right. Now, what do you do once you have the Cholesky factor G? To solve AX equals B, forward substitution, GY equals B, so it's like with LU. And then G transpose X equals Y, but back substitution, so that's like solving UX equals Y. So the process is very much the same. It's just that the two matrices involved are transposes of each other. Okay. Like I said, symmetric positive definite matrices, you can compute LDLT. Now, LDLT does not require any square roots. So it's actually known as the square root free Cholesky decomposition. And it turns out that the Cholesky decomposition and the LDLT factorization are very closely related. So you can express one in terms of the other. Okay. Cholesky factorization is unique, and the fact that the diagonal entries are positive is that assumption is necessary to give you uniqueness. Because when you take a square root, technically you can choose a positive or negative square root. We just always choose positive. If you want a Cholesky factorization in MATLAB, Chol does that. There's also an LDLT function, by the way, for that factorization. But one thing I want to mention is that there's two different ways of writing Cholesky factorization. There's this way that I use. A is lower triangular times its transpose. Or you could write it this way, A equals R transpose R, where R is upper triangular. So it's still lower triangular times upper triangular. It's just different notation. So MATLAB follows this convention. So if you call Chol to get the Cholesky factor of A, it's going to give you R, and then you'd have to transpose that if you really wanted G. So no big deal. This is no difference in notation conventions, but something I want to make you aware of in case you end up actually using its function. So different books just use different approaches to writing it. I should mention that my advisor from Stanford, Gene Golub, so the computer in his office, its address was cholesky.stanford.edu. So, okay, well, we're just about out of time. I'm sorry that I ended up taking too much time because I was hoping to have time for homework questions, although certainly if anybody has them, they're welcome to ask, or if you can also stay and ask after everyone else goes. But does anyone have questions of any kind, homework or not?
I have one more question.
Okay.
Okay. 3.41.
Wait. 3.4.
1. Yeah.
Okay. All right, let me navigate there. Okay, I need to unshare and reshare. Are you talking about this?
Yes.
Okay.
Okay, so I'm not sure what you do exactly. You said show that if this norm is less than 1, then A plus this matrix is non-singular. So I'm not sure what to do with if you can just explain how to go about this, because I used the properties of non-singular matrices. That if a matrix is non-singular, then an inverse exists. So using A times B equals to identity, and B is the inverse of this matrix. And then I tried to multiply both the matrix and its inverse, and I came up with some kind of weird formula.
Yeah.
For the inverse of A plus E. I don't know if the formula is correct, or maybe that's why I'm getting it wrong. So like I was trying to find the inverse of when we add to matrix. Say we have A plus a matrix A plus B. I want to find the inverse of A plus B. Is there any way we can do that? And I came across, I think, Sherman Woodbury formula, something like that. And I tried to use that idea to kind of, because they didn't give us directly. So I was trying to use what they did there to get a formula for A plus E inverse.
Okay.
I don't think the formula was correct, though.
Yeah. I need to interrupt you because we're past time and people might need to go. But I was like, I need to steer towards a different approach, so that will put you on the right track for this problem.
Okay.
I want to do this quickly because people have to go.
Okay.
All right. So what you can do is use the fact that, okay, I'll make a note of it here, and I'll add this to the notes before I post them. Oh, not a sticky note. Shoot. Sorry. Okay. All right. No, stop that. Sorry. It's being stupid. Okay. So I want to get rid of a sticky note. All right. So if A is singular, then AX equals 0 is satisfied for some non-zero x. So what you can do is assume AX equals 0, or not A plus epsilon E, x equals 0 for some non-zero x, and then show a contradiction. By taking norms. Now, I'm actually going to talk about norms next class. And actually, that means I think apparently I needed to reconsider the due date of this assignment for that reason, because I just realized that I'm covering material from the assignment on a day that it's due. Like, whoops. So I'm sorry, I messed up the calendar there. So certain properties of vector norms that will be helpful for this problem are what I'll discuss on Monday. So I will update the due date this assignment in light of that. Okay. All right. We are well past time, but I will add this to the notes before I post them tonight.
Okay.
Okay. All righty. And everyone else, well, several of you I will see in the next class period, but otherwise you're welcome to Scram. Let me stop the recording now.